Great. All right, let's get started. So, Quantifind story: building custom interactive data analytics infrastructure. So, a little bit of background. I'm a software engineer for Quantifind. I mainly focus on our core infrastructure backend, which most of our data analytics products are built upon. You can reach me at those channels. So just a brief outline of the talk, right? We'll talk briefly about what does Quantifind do, some of our core technical challenges. Then we'll look at 3 motivating use cases to have in mind as we discuss the existing solutions that we tried to address those use cases. And finally, the bulk of the talk we'll talk about some custom infrastructure that we've built in-house. And finally, leading up to some of the lessons that we've learned and talking about why we decided to build something custom and sort of stepping back and asking the question, was it worth it? Was it worth it to go custom, right? So, so what does Quantifind do? Quantifind tries to find intentful conversations. So conversations, basically chatter, that correlates to a customer's KPI or a key performance indicator. And then we take that and we try to surface up actionable insights, something that a customer could actually use to affect their day-to-day business. So the input for this is sort of a vast amount of consumer comments in the form of tweets or Facebook comments or other sources that are available. We also analyze third-party financial data that goes along with these consumer comments. And the output are the top-level actionable insights, and what we're also aiming for is providing is interactive exploration for the customer. So let's talk about some of our technical challenges. So talking about specifically the consumer comments that we have, right? There's a multi-terabyte annotated data set that contains billions of conversations, of comments, from millions of users, annotated in hundreds to thousands of different ways. When I talk about annotations, I mean things like, that maybe a geographically tagged annotation or time zone information or demographic, for example, things like that, gender, ethnicity, etc. So what do we want to do with this data set? So we want to slice and dice and compute over many different dimensions. And one of the things to keep in mind as we talk about some of the motivating use cases is it's pretty hard with a data set of this size to sort of pre-compute everything, right? Pre-compute all answers for any questions that we can imagine asking of this data set. And we want to do things at the user level. So when you do things at the user level, it's just quite tough to sort of go this sort of pre-computed route. So just have these challenges in mind. So 3 motivating use cases. So Quantifind does, we do a lot of different things with this data, but I'm just going to highlight 3 use cases or 3 workflows that we have in our business. So one is we want flexible time series generation. Another one is we want in-gram co-occurrences. So essentially sliding window groups of words that co-occur with another word, and I'll dig into that in a little bit. Another one is cohort analysis, so trying to do analysis on a particular highlighted group of users, if you will, that happen at one point of time, and then trying to study those users over time in the future. So let's talk about time series. So what we want to do is generate a time series of conversations, right? So if you look at this graph, it's essentially just a time series of social chatter over a certain period of time. So there are many different time series databases out there that you can just kind of send it a whole bunch of data and it can very quickly give you a time series. But we're trying to do different things. We're trying to do some interesting things here. So for example, we want flexible or arbitrary binning, right? So we want to be able to zoom in at any different level, year, month, day, hour, down to the second. But within each of these bins, we want to have the flexibility to do custom logic. So in this case, it's user deduping. So that means, for example, if this is a time series of people talking about the movie Gone Girl, for example, we may only care about within a particular bin. So let's say within a day or a month, we may only care about a user mentioning Gone Girl once within that particular bin. So this helps us with doing sort of on-the-fly spam detection type stuff. The other thing is we want to be able to generate a time series over our data that matches different dimensions. So one would be text. That's a very simple one, right? Give me a time series of of people talking about Gone Girl, but maybe talking about Gone Girl from here in California, for example. So we want to be able to very quickly specify which dimensions we want to generate the time series over. So moving on to n-gram co-occurrences. So I'm not sure how many people here are familiar with sort of the natural language processing, but this notion of n-grams comes up pretty frequently, where n-grams are nothing more than a sliding group of adjacent words in a document. And a document in this case is just text, right? So I thought I am hungry right now might be fitting since lunch is coming up in a little bit. But so an example of n-grams would be for I am hungry right now. The 1 grams would literally just be the single tokens. Bigrams or 2 grams would be I am hungry, hungry right, and then 3 grams going up to whatever n-grams that you want. But one of the things that we like to do is, well, first of all, computing the n-grams, that's one thing, but we also want to be able to find co-occurring n-grams for something that we care about. So in the case of this, we might, the search term might be hungry, and so we want to find all n-grams that co-occur with hungry, right? So this could be am hungry, hungry right now, but you can see, for example, we would return right now, even though it doesn't have the search term in it, because right now co-occurs with hungry, for example. So this is something that we, this is a use case that we have, and we want to do it over large amounts of data. So, so cohort analysis is another use case. So the basic idea is we just want to capture a group of users matching some criteria, and then we want to analyze their conversations, analyze their chatter over time at some other point in the future after they were exposed to some event. So a concrete example would be capturing users commenting that they're interested in seeing Gone Girl, after seeing some advertisement about it or whatnot, and then after the movie is actually released, figuring out or doing analysis on that same group of users that expressed interest in seeing it. What are they talking about after the show actually airs and you can see it in the theater? So there are a whole bunch of, this is just one example, I'm using movies as an example, but there are a whole bunch of implications here when you talk about sort of campaign analysis and things like that. So now we'll talk about some of the approaches that we've tried, right, to solve these use cases and many others that we have. We'll talk about briefly Spark, Postgres, and Elasticsearch. We've also tried others, but just for the sake of time, I'll just briefly talk about these 3. So with Spark, so Spark has worked out great for us in asking sort of ad hoc questions about our data set and whatnot. We did experience certain challenges when trying to compute n-gram co-occurrences on our existing 12-node cluster that we have. So granted, it is a bit of a smaller cluster, and we're not using the latest and greatest version of Spark. We're using a somewhat older version of Spark. But one of the things that we also found was it's sort of tough to reduce the search space. So this is another theme to sort of have throughout the talk is the search space, right? So the entire search space is the entire multi-terabyte data set. But a lot of times we only care about certain sub-regions of that data set. And so what we ended up doing with Spark was essentially taking our data set as it exists on HDFS, on disk, and sort of breaking it out into different sub-components and then feeding just those smaller components into Spark and doing analysis. So that's a little bit tedious because many different people within the organization have different, and the products themselves have different use cases. And also, somewhat of a challenging developer experience. So Quantifind has, we also have a team of data scientists. We have, a client services team. The core developers work very closely with the data scientists to actually build products. And we all sort of had a need to ask questions of this data set or do analysis on it. So there was some contention for cluster resources. Sometimes I'd come into the office and someone would say, oh, damn, I'm just waiting for to submit my Spark job, waiting for resources to become available. And a lot of this can be addressed if you switch to Yarn or Mesos, but we just didn't have those resources internally. We were just using Spark in standalone mode. Also, when you make code changes, imagine that you're trying to build maybe a model and you want to change coefficients, et cetera, and you want to be able to just quickly rerun your model. A lot of times that can involve repackaging your Spark program and sending it out to the cluster. So it's a little bit of a tough developer experience. So then we thought, well, okay, we sort of know what our data set what our data set is composed of, and we know the categories of questions that we want to ask the data set. So we thought, well, let's take a look at Postgres. Let's see if we can shard the data set by vertical, so for movies, for example, or restaurant or beverage, depending on the category of data that we're talking about, and also time. So that was great because we could ask, if we only cared about a particular year, we could actually just reduce the search space, going back to that, and only find tables that would have data for that particular time period. But the way that we had Postgres running was still on one box. It was a very beefy box, but we found that query performance still suffered greatly when we had a lot of concurrent requests coming in and hitting different shards within the overall schema. Also, just managing the table partitions is pretty painful. It's not really supported. The management of the partitions is not really part of Postgres. There's a third-party plugin that someone wrote, which goes a long way, but it's still somewhat painful to manage those partitions. The other thing that was really limiting was, so it's great, SQL-style operations are great for basic questions, but when you want to start doing on-the-fly statistics or custom operations, it's really hard to sort of move that computation to the data if you want to go beyond your SQL query. And so that's one of the things that we ran into. Also, we also briefly tried Elasticsearch. I would say one of the main things that so Elasticsearch is great for just quickly retrieving documents and finding hits and things like that. But we found that going back to moving computation to the data, we have a need to do sort of custom statistics, custom analysis, and it's hard to sort of shoehorn that into a system like Elasticsearch. Also, rebuilding the indexes could be a bit annoying at times. So stepping back, what do we really want, right? We really want to take our data and keep it in its rawest form and hold it in memory, right? That's the key thing here. So that we can build custom analyses. So for example, time series, cohort, n-gram co-occurrences, and many others. When you have your data in its raw form, and it's not aggregated, you have way more flexibility to ask questions about the data. We also want the operations to be on the fly and optimized. So one of the pain points, going back to sort of changing some coefficients of your model, for example, and then rerunning it, we really wanted to change our workflow and avoid having batch jobs that would take hours to run in order to get results back. So we wanted to step back and ask ourselves, can we build something that would be more optimized, more on the fly? So we thought, well, let's take the data. It's in a verbose format, but let's see if we can pack the data in a custom way and jam it in memory, right? Well, it can't actually fit on a single machine. The data set that we have, and it continues to grow at rapid rates, it just can't fit in a single machine. So we thought, well, let's step back, let's compact the data in memory across multiple machines and use Akka Cluster for the communication between these nodes. I'll talk more about Akka Cluster in a slide or two. So once the data is sitting in memory across multiple nodes and they're communicating via Akka Cluster, we can make scatter-gather style requests against the raw data and compute things on the fly. So this means we're no longer trying to shoehorn our use cases with the API that's provided by an existing open source package. We're sort of only limited by the custom Scala code that we can write. So what we developed was something called, internally, we call it RTC. It stands for real-time cluster. Not real-time in the sense of like Storm or something like that that's trying to do computation sort of as data is coming into the system, but it's really real-time in the sense that it's interactive. You ask a question and you get the results back within milliseconds or seconds. So just briefly talking about this, we'll go into more detail on each of the components in a minute, but these are, just stepping back, these are all actors living on different machines. So the RTC workers are living on separate nodes. The master is living on a node, and the API handler is sort of an extension of the master. So a request comes in, so going back to the use cases, let's say we want to do a cohort analysis, or we want to generate a time series, or do n-gram co-occurrences for some slice of the data. That comes in the form of an HTTP request. So we've developed a very flexible HTTP-based REST API to describe the types of queries that you want. And it's a language that we have and we own, so we can customize it as we see fit. The request comes into the master, and the master essentially does a scatter-gather style operation to ask the same question that was asked of the master asks each of the workers, right? And each of the workers has their packed data, their slice of it in memory. And the workers go and they do their computation on their slice of the data and then send it back to, do some worker-side aggregations and then send that back to the master for the final roll-up and send it back to the client. So digging into some of the RTC components, I don't have it on that diagram, but there is a pack file writer, the thing that actually generates the pack files, the master, and the worker. So the pack file writer is an offline job that consumes the raw annotated data set and builds these .pack files. So what are in the pack files? It's the data that was in the human readable data set, but in a packed custom binary protocol that we've developed for our data. It also packs the data such that it's easily distributable across the RTC workers. So you can, essentially what the master does is when it sees that there are a group of pack files to give out, it just says, okay, first worker, you get one, second worker, you get one, third one, you get one, and then it just goes back in this round robin fashion. But the pack file writer is breaking up the data in such a way that you usually don't have one worker that has a bit more loaded in memory than the others. So the master, as we mentioned, handles the incoming request, kicks off the scatter-gather style operation against the workers. One of the other things that the master does that we found that was really helpful was it has a fairly sophisticated caching mechanism. So depending on which permutations you're asking, for example, I care about users talking about Gone Girl within the first part of 2013, matching this particular search term, maybe mentioning popcorn or something. And so you have these individual permutations of requests, and those things can get cached in LRU caches, so that you can avoid going and asking the workers for the answer when the master has the answer already. So the workers start up, they register what they find the RTC master via Akka Cluster, and the master says, hey, you should go and try to load these set of pack files for yourself. So the workers go over to HDFS, read the pack files, and jam it into memory, and it continues to handle the request from the master. So just digging into Akka Cluster, I'm not sure how many people here have used it before, but it is a really wonderful package that is available for us from the great guys at TypeSafe. So if you are used to doing scatter-gather style operations within a single JVM, doing that across JVMs with actors running on two different JVMs becomes a really nice extension point. One of the huge benefits of going with Akka Cluster is we don't have to worry about the network layer. Akka Cluster tells us when a worker goes down, or it tells us when the workers can't see the master, for example. So it sort of shields us from these things that you would normally have to deal with if you're trying to build something like Paxos yourself. So we found this to be really helpful for us because we can focus on the core logic and how we pack things in memory within RTC. So let's go back to how we compact the data, right? So I mentioned we have a custom binary protocol. Each record has a fixed header with a set of fields and values. And we have annotated user records and annotated comment records or tweet records, and those are packed separately and then they're joined on the fly. So I will talk about, there's also another theme here, which is essentially one of our goals is trying to not visit data in memory that we don't need to visit for the current request. And so separating these things out is one step forward in that direction, and I'll talk more about that in a minute. So here's a start of a custom protocol. So there's a header that's 2 bytes. For example, we can take the user ID, which is a long, we can pack that, followed by the timestamp. Also, like the tweet text itself is also packed in this way, and so we need to have a way to specify the number of text bytes that we have than the text itself. Terms are really just the original text. Like I think earlier I had, I am hungry right now. So what we would do is we would take that text, we would break it up into multiple tokens, what we call them terms, and then we would 64-bit SIP hash those things, so that it becomes easier to do sort of on-the-fly binary searching, and I'll talk about that in more detail later. One of the things that we can do, because we sort of own the format, we're not tied to JSON or some other existing format, is that because we understand our data and how we can compact it, things that would normally need to get represented as an array of values or of unique values, we can sort of bit pack them into smaller values in a byte or a short, for example. So the data is compacted in this form in the pack files on disk. Moving on, so let's talk about garbage collection. So I'm sure everyone in this room at some point has gotten an out-of-memory error in the JVM, right? Either you're aggressively allocating too many objects, or you have one object that is taking a very large hash table or something, and your JVM just sort of craps out, right? So the JVM is great for the happy path. When you're not, the garbage collector, for example, is great for the happy path. When you're not explicitly managing your memory and you're not worried about allocations, right? It's sort of nice to be able to write a case class, instantiate it, and do some operation with it, and then move on to the next bit of work that you might have. But the garbage collector can really get in your way when you have large JVM heaps with a lot of objects. The garbage collector, despite many advances in JVM garbage collectors, they can still create pauses that can affect your application's performance, right? And going back to the original diagram where we had the HTTP handler going to the master to the workers, the goal really is to submit an HTTP request and get back the answer as quickly as possible within seconds or milliseconds. And to really achieve that, you need to minimize your garbage collection pauses, right? So how can you store a lot of objects in the JVM that need to live around for a long time, but without sort of upsetting the garbage collector? And what we came across was storing it in off-heap memory. So I'm not sure how many people are familiar with unsafe, but it's sort of this backdoor that the JVM provides for doing C or C++ style memory allocations. There are many other things that unsafe provides, but one of them is sort of a direct channel into sort of doing malloc C-style operations. So the nice thing about using unsafe is you can use it to allocate a chunk of memory, and the garbage collector essentially doesn't see it. So it doesn't try to mark, which objects that are contained within that, what's the life cycle, are they still around? So it drastically reduces the pressure, GC pressure that you would normally have. However, memory allocated via unsafe must be explicitly managed by the developer. So that includes deallocating it, figuring out exactly how you're going to lay out your objects. We sort of take that for granted. When we create a bunch of objects on heap, the JVM figures out how it should allocate that and takes care of compacting over time as the garbage collector runs. It takes care of shifting things around in the heap. But when you start to use unsafe, you have to do that entirely yourself. Visiting the real-time cluster diagram again. So the thing that changed is at the bottom. So before we just had packed data, but now each of the workers are maintaining their portion of the pack files, the data, the social comments that are in the pack files, and storing it in various off-heap regions on each of their JVMs. So let's talk about working with off-heap data. So I mentioned this earlier, but one of the really important things that we found was when a request comes in, we really only want to visit the data that we need in order to satisfy the current request. So this means never materialize data that you don't need. So imagine a request coming into RTC, and let's say you're just doing a time series, but you're not caring about users mentioning the words Gone Girl or popcorn, but you really just want a time series very quickly of people just talking in general, right? So you don't need to visit the text at all. So in this case, you really don't want to parse the text and bring it over into the application space, because one of the things about the JVM is when you have a string in the JVM, there's a little bit of extra data. If you look under the hood of the string class, you can see there's a little bit of extra data that's being carried along apart from just the raw bytes that would make up the text, right? So it's really beneficial to not read the text if you don't have to. So let's look at this code snippet. So imagine that you have a timestamp method, right? So normally, if this is a normal case class, you would have a long value. That's part of your case class definition. But when the data is stored in off-heap memory, Unsafe provides a getLong method. And what you do is you give it a memory offset of where you can find an 8-byte long. And so what we're doing here is we're saying unsafe.getLong, we're skipping past the header, which was 2 bytes, and we're skipping past the user ID, which is 8, and we're extracting just the timestamp value that we need. So in this case, we don't have to, so imagine, I don't have the example here, but imagine if what was before the timestamp was the text. We can essentially just skip over the text and pull just the timestamp out. And that's just less temporary objects that the JVM has to deal with. So we only access the fields that are needed for the given request. In the case of engrams, for example, engram co-occurrences, we might not necessarily care about time, but we do care about the text. So we can skip past all the other data that's there in the records and just grab the text and do manipulation on it. So another example, this is a little blurry, I hope you guys can see it, but another thing to keep in mind when you're doing off-heap, when you're manipulating off-heap memory, the game changes a little bit. So most of us have used java.util.arrays.binary search, which requires having the array materialized, right? And if these sorted arrays are very large, it's just extra allocations that you have to have on heap. So what we've done is we've written our own binary search method that works directly off heap. So don't worry about following all the details here, but the highlighted getLong is sort of the key takeaway point here, that so you can imagine this sorted structure of items living over in off-heap memory, but you don't want to bring the entire array on heap. You just want to visit the items that would be matched by the normal binary search operation. So here we're doing getLong. We have the initial offset of where we can find this array amongst a sea of other data. And then based on whatever the current midpoint is, we can multiply it by 8, because in this case, the things that we're searching are longs. And then we can find the values that we want and actually do the binary search without having to create a whole bunch of extra objects. So the search space, right? So each worker, going back to the other diagram, each worker has a portion of off-heap memory that it's managing. It also, as these workers start up, they build these various arrays of different data structures of offsets pointing to records in off-heap memory. So when a request comes in, the worker looks into these data structures and figures out which memory offsets it needs to use in order to satisfy the current request. However, there can be, depending on the type of request, like if you're only asking for a month, a time series for a month, or engram co-occurrences for a month, chances are you will have maybe thousands of offsets. But sometimes we want to do analysis over multiple years, 4 or 5 years of data. And so in that case, you have millions of offsets that you need to hone in on and access an off-heap memory. So there's a need to do this as quickly as possible, because remember, it is a real-time system or interactive system where you make a request and you want an answer back. We want to avoid those hour-long batch jobs, right? So what the workers do, so the added item here on this diagram is the facet indices. So what the workers do is they have their off-heap data sitting on one side, and then on heap, they have these various arrays of offsets into the off-heap data. So when a request comes in, the master asks the workers, can you generate a time series over this particular period? The workers can quickly look up in the facets if the query had something that would benefit by having a facet index. If there is no facet index for a particular query, then it is sort of a full scan. It's a full scan of all offsets. Excuse me. But if the query does mention something that has a facet index, we can use it. So an example of a facet index would be something like time, right? Most of our queries actually do care about a particular time range. We either want to make statements about a year or a month, a week, et cetera. So how can we avoid visiting data or searching data that isn't contained by the current time span of the given query? So if we only care about 1 week, how can we avoid looking at all the other data that did not occur within that week? So one thing that we can do is we can build, just use the data structures that we have available, but use them in interesting ways that allow us to figure out which off-heap offsets we need to satisfy the current request. So what we can do is we can build a tree map of a long to an array of long. The keys are the timestamps in this particular case. The timestamp of, so if I tweet something now, the timestamp that's associated with my tweet is potentially a key. We do some other things where we sort of round the timestamp down to avoid having very large tree maps. But you can think of it as this being a timestamp. The values are offsets to records sitting in off-heap memory. And the nice thing about this is we can do range-style operations. So we can ask the tree map for this particular week or this particular number of minutes, for example, very quickly give me the arrays of longs or the offsets that could possibly contain the answer for the query that I'm asking. So this greatly reduces the search space, because remember, we're dealing with multiple terabytes of data, and if the answer is just sitting in 5 megabytes of data, it's way faster to look at the 5 megabytes as opposed to the all terabytes of data, right? So I mentioned that we want to do these things very quickly. So the way that we've structured this is, once you have the array of offsets, we essentially unleash a group of threads over different portions of the array. So we don't take the array and break it up into mini arrays. We just take the array and we find the proper start and end indices of the array and say, okay, so thread 1, you get this start offset and that end offset. Thread 2, you get this particular range. And so in this way, multiple threads can sort of attack the array and corresponding off-heap lookups in parallel, and then merge their results. So essentially what's happening here is, in the case of a time series, you can think of the value being an atomic integer, and what's happening is these threads are attacking the array, and they're each incrementing some shared atomic integer, and finally sending that back to the master, and that's within one worker. So there's this tweet from Kelly Summers, who's sort of a champion in the infrastructure space, that sort of caught my attention while we were building RTC a few months ago. So I hear about how immutable structures are awesome, but here's the thing: you want millions of operations a second, you need to stop allocating memory. And this sort of really hit home for us, because one of our key things that's sort of the most important thing when we introduce a new type of operation in RTC is, how can we limit the amount of allocations for that current request? Because the reality is, for some types of queries, we actually are hitting millions of offsets, millions of operations. We're doing millions of operations within a very short time span, milliseconds. So we want to really avoid creating unnecessary allocations and having the garbage collector get in our way. So that was just a quote that I thought was germane to the talk. So let's talk about some of the lessons that we've learned. Reduce allocations as much as possible. Avoid large JVMs, but not only just large JVMs, because you can have a large JVM with very few objects and it won't get in your way. But large JVMs with many objects stuck in the tenure generation or the permanent heap can be really disastrous. One thing that we found is some of these requests can do computations that are fairly expensive, depending on the math that's going on for the given request. So we found that keeping things around in LRU caches was very helpful. However, that also can come back to haunt you, because if you have an LRU cache of 1,000 elements, the only way that things will really get evicted is when you push something in a new element that would evict an existing one. So what we found was that for some of these LRU caches, we were storing values that actually took up quite a bit of memory, but didn't need to be around, right? They can be recomputed on the fly. So what we ended up doing was wrapping those LRU cache values in soft references, and then the JVM can decide, oh, I'm experiencing some GC pressure, so let me forcefully pluck this item out of your cache for you, right? And then the next request that goes in that tries to get it would just recompute it. Another thing that we found was chunking, and Akka is really great for this, and Akka Cluster is being able to take an operation that would otherwise cause the workers to hold a lot of data and intermediate data on heap. We found that in order to mitigate that, we could take a very large or expensive request and introduce chunking within the actual request. So the main request to the master is morphed into smaller requests that get sent to the workers and then finally aggregated. We found that this offered more concurrency in the system. We also found that, Scala collections are really great. It's really nice to be able to do filter, flat map, for each, et cetera. But what we found was, in particular, the data structures that we use to store some of these facet indices, it ends up being a little bit more efficient just from a memory standpoint to use trove collections or even just drop down to primitive arrays. The nice thing about the actor model is that internally within your actor, you can use mutable data structures. You can use trove maps or Scala mutable maps, whatever you want, but the messages that end up going back and forth are immutable. So it's the actor sort of protects you or it doesn't require that you use immutable data structures internally, which we found to be nice. So was it worth it building a custom solution? Yes, it definitely was. So we're able to take the requirements from our business. Some of these cases are very challenging, and we don't have to sort of say, how can we do this in Spark, or how can we, twist Postgres to answer this question for us. We can build it ourselves, right? We can build the custom functionality ourselves within RTC. So we're able to adapt to new requirements from the business and less shoehorning. Some future improvements. This is sort of a core piece of our infrastructure now, so we're constantly adding things to it, but just a couple of things. We want to add more redundancy and scalability, and the nice thing is that Akka Cluster does a lot of this for us. Akka Cluster is firing off all the signals and telling us what's happening at a network level, but we have some work to take more advantage of that and deal with failures better, deal with cluster failures better. We want to explore even more ways to compact our data, right? Store even more of our data, different data sets, financial data, or anything that we have. Being able to come up with even a more compact representation so that we can store even more in memory and do more on-the-fly computation. And as hardware becomes cheaper, this becomes more feasible. I really think that you don't have to be going to a batch Hadoop job for every type of analysis that you have. I think the way that hardware and memory is becoming cheaper and cheaper, it will allow us to do more things like this, right? So, summary of the talk. Akka Cluster, non-aggregated off-heap data, and fast custom Scala code was a win for us. Thanks. One other thing is, if this is interesting to you, we're also hiring. We're hiring for data scientists and back-end engineers like myself, so see me afterwards if you're interested at all. Any questions? Yes. Yeah, so we're actually not running in EC2, so it's a little bit harder for us to take advantage of some of the things that Amazon provides. We're sort of running our own data center. But so I'm not sure, I don't know too much about Redshift if they have sort of a custom programming model, but we found that a SQL-based query language got us, it answered a certain percentage of the questions that we want, but there was a need where we were like, there was some particular algorithm that we developed internally for our predictive analytics, and we wanted to bring that as close as possible to the data, as opposed to getting data back from a system like Redshift and then computing over it. We want the computation to be sort of in the system so that you're still returning very few results. So that was, but that's something. I mean, one thing that I should also mention is that we're always looking at other technologies that are there. We're not sort of giving up on anything. We're always keeping an eye on it and trying to track the evolution of all these other products too.
Yeah, could you talk a little bit about the project to build this? Like how long you spent on it to do prototypes? How big was the team?
Yeah.
Even what the cost you think might have been?
Yeah, definitely. So a little bit about the evolution of it was, we were just sitting in the office one day, and one of our other engineers just sort of, grabbed myself and another engineer, and he was like, how can we do, how can we solve this use case, but like really fast, right? Like there was a lot of pain that was experienced. And so we sort of stepped back, and the first one was just on a single node, just taking the data that we cared about and putting it in memory on one JVM. And then I think it was just over the weekend, I think some of the Akka Cluster guys are here. I think they, when it was announced and further developments were like, I knew I always wanted to play with Akka Cluster, but I never really had a use case. And then sort of the two ideas just sort of came together over the weekend, and so the quick prototype took about a week and a half. But the project has been going on for, I would say from beginning I think it started 8 or 9 months ago. So things like Akka Cluster and Scala itself just really helped us to do this very quickly.
How many devs?
So the core was built by myself, but then since then it's been I think two or three other engineers have since come on, but the core was essentially 1.5. Hi.
In RTC Master, did you have a use case where you basically want the answer to a series of questions whose output depends on each other being completed, and how did you resolve that?
Yeah, so we don't have chained questions and answers, request responses. But one thing that we did build was batching. So you can actually fire off, thousands of questions to the master at any one moment, and then the master will take care of, farming it out and grouping the same results in the same order that you asked it. But I would say the closest to that use case would be the cohort analysis, because you're asking for, give me like a time series of something that's happening now, but a previous query must have been satisfied. And the previous query in the Gone Girl case was people actually talking about Gone Girl at some point in the past. So that is one case where it's sort of two dependent queries morphed into one. But we have a lot of ideas to build that type of stuff, and we can sort of do it because it's custom. It's something that we build internally. Hi.
It sounded from your description like a lot of what you did was based on the assumption that you had relatively few schemas and they evolved relatively slower over time. What sort of solution would you recommend for a problem where there are, say, more different kinds of data, or the data schema is expected to evolve week to week or month to month?
Yeah, so we definitely took advantage of the fact that our schemas don't change that frequently. I would say, one other thing that we looked at for the custom protocol was something from Google called flat buffers. I'm not sure if you guys are familiar with it, but flat buffers also, let you specify your schema definition, and then they generate a bunch of code but it doesn't look in off-heap memory. It looks in just byte buffers. So you can do something similar with byte buffers, but and sort of sliding to the right offset with byte buffers. But we found that going with unsafe directly was the fastest. But yeah, that's just one thing that we haven't had to come up with. But I think if we found ourselves in a situation where our schema was changing rapidly, we'd probably end up building a tool or maybe revisit flat buffers or something like that. Mm-hmm. Hi.
What kind of bugs do you see? What would you do different if you had to do it over again?
Wait, so what kind of bugs do I see?
Two questions.
Okay.
What kind of bugs are most frequent in your environment that,
Yeah, definitely. So I would say that, once, so I'm just thinking, there are many different things that have happened over the lifetime of RTC, but I would just say the most recent thing was the LRU cache thing that I mentioned. So we were essentially storing off-heap offsets based on some cache permutation, and sometimes the arrays were very large, right? And so that would introduce GC pressure, and there was no way to get those guys out of the system. So what we would see is some workers would actually have out-of-memory errors because what they were storing on heap was too large. And so the way that we controlled that was by using soft references, and the system has been tremendously more stable since then. Hi.
Can you describe your data ingestion mechanism, how you're actually acquiring the data to put into this?
Yeah, definitely. So we have, so all this data is well, apart from the third-party financial data, is freely available. We have our own Twitter streamers and Facebook crawlers that we have that ingest the data from the social space, and it goes through its own Hadoop pipeline that happens at night to actually take the raw data and output it in such a way that it's still the raw data, but it has a bunch of other annotations. So we apply our trained machine learning models on the raw data, and then the output that I mentioned was the annotated data set. So that's where RTC sort of starts. So you take that packet and then it goes into memory.
Is that just like a sequence file that you store in HDFS, or?
It's not yeah, so it's stored in HDFS, but it's not a sequence file. It's literally just something that just writes out the raw bytes. That's it. And then we just read the raw bytes on the way in and just shove it into off-heap memory. Yeah, I'm not sure how, yeah, maybe we have a couple more questions? Hi.
So you mentioned you wanted to let users dedupe their data. So how did you handle database consistency getting in, when you were loading it into memory like that?
So when I say deduping, I meant, so let's say that, for this, let's say today, I go and I tweet, I love Scala days 1,000 times, for example. And then if I want a time series, if I want a deduped time series by day, I don't want myself to get 1,000 votes for I love Scala days. I want only one vote, right? And so that's where the on-the-fly user-level deduping happens. And we've come up with some ways to really optimize that so that you can do custom operations while you're generating the time series and you're not just regurgitating, points in the system. Hi.
How do you handle skew for requests hitting some workers really heavily?
I think the skew happens sometimes we can't quite balance the data that's loaded in memory across the workers that well. That's actually one of the future things that we want to do is come up with better balancing algorithms. We try to do a pretty good job of it, knowing the number of workers that we have in the system. By the way, we have 10 workers, 10 nodes in the system right now. So we try to do a good job of sharding it properly on disk, but there's still certain things where once it actually gets put in off-heap memory, some worker might be skewed, from a memory perspective. And in that case, that's just, it does affect query performance, and depending if you're hitting the data that happens to be more heavily skewed on one worker and not the other. But for most cases, it's not a problem. Hi.
I'm curious how big your cluster is, how many nodes.
Right.
Also, how are you monitoring your nodes?
Yeah, definitely. So it's 10 nodes, 10 machines, and what we found was that we have 10 machines and we have 2 worker JVMs on each machine, stacked on each machine. So 2 different JVM processes. Each JVM is 8 gigs, and then of course, it allocates, a lot of off-heap memory per machine for the actual packed data. And in terms of monitoring, I think our DevOps guy could probably speak better to that, but we have, in Nagios, he has it set up where we can, or I forget the exact tool that we're using, but we can see memory utilization, CPU utilization, and we also have counters that we have built in, so we can keep track of, request statistics and things like that. Yep. Cool. Hi.
How do you handle node failures? I did see you talk about data redundancy.
Yeah.
So is that you just recover a new node and load the data back into memory?
Yes. So currently, so that's one of the future things that we want to improve. Currently, when a worker dies, there's no one else that's holding a copy of their data, right? That we could move into a system like that, but what I'm leaning more towards is having workers that are on standby. So using Akka Cluster, we can find out, oh, this particular worker died, and it did have these set of pack files loaded, so let this worker move into its position and then reload the data as quickly as it can. That's fine for our current use cases, but if we move to a world where, we need uptime, we can't afford to have any downtime, then that would be something where we need to sort of think about maybe having, standby workers or, these things are a little tricky, right? Because you can start trying to end up building your own Hadoop or your own Spark, for example, and that's not what we're aiming to do at all. This thing was built very custom, very specific for our use cases. But, as the use cases arrive, we will add the complexity as we need, as required. Hi, maybe the last one. I don't know if you guys want to get lunch. Yeah. Hi. So we rebuilt the data set every night, but currently we only refresh RTC on a weekly basis, but the plan is to move it to sort of a nightly refresh. There is also nothing stopping us from updating on the fly, where we have more of a real-time stream of updates, and we're updating the in-memory, off-heap in-memory on the fly. That's just a whole can of worms that we haven't really needed to address, just because it's not a business use case. All right, cool, thanks guys. Yeah, you can ask me afterwards. Thanks guys.